All right, so let's look at these two free response interval of convergence questions that I gave you all to do. First one's from 2010. You have a Maclaurin series, which at the moment you don't know what a Maclaurin series is, but that's irrelevant for the first part of this question. And the interval of convergence will always be found, I shouldn't say always. In this case, we will use the ratio test. The only time you don't have to use the ratio test is if you happen to recognize that the series is a geometric series, and then in that case, you wouldn't have to do the ratio test. You could just set the ratio less than 1. So to do the interval of convergence, you'd have to set up the limit of the n plus first term divided by the nth term. I've gone ahead and set that up to save time. You do have to write this whole thing in detail because part of the points they give you is just for knowing and setting up the ratio test. Now, eventually, we should know that the negative 1s to the n and to the n plus 1 will completely be irrelevant because of the absolute value. So I'm going to go ahead and get rid of those because absolute value will determine that those negatives are insignificant. My 2x's, I have one more in the numerator than the denominator, so I'm going to cancel all but that. The n minus 1s do not cancel, and so that will give me a reduced version of this limit of 2x. The 2, if the absolute value of 2 is 2, the x can be negative, so I'll keep that in absolute value. N minus 1 for n starting at 2 will always be positive, so I'm not going to worry about that being an absolute values in the denominator. I only have an n. And if you look at this limit, this is a limit as a function of n. Top and bottom degrees are equal. We have n to the first, so the coefficients, the ratio of the coefficients is the answer to the limit. So that will be a final answer of 2 absolute x. And in the case of a ratio test, we need the answer to the limit 2 absolute x to be less than 1, which will be when absolute x is less than 1/2. And while this question did not ask you to do this, if it did ask for the radius of convergence, you would stop right here. Your radius is actually 1/2. Anytime, whenever you get to the absolute value less than a number, that number you are less than is the radius. So now I know that my center of this series is 0, and my radius of convergence is 1/2, which means I can go 1/2 a unit in each direction. And for everything between negative 1/2 and 1/2, I'll converge. What we now have to do is test those endpoints. And so we will simply replace the x with a negative 1/2 and a 1/2 and determine if this series will converge at either of those endpoints. Okay, so I have plugged in negative 1/2 and 1/2 for x to get these two series. I'm going to simplify both of these real quick. Negative 1 to the n times negative 1 to the n is negative 1 to the 2n, which is the same thing as negative 1 squared, which is 1 to the n. And this is going to happen over here also. 1 to the n is just equal to 1. And so for this one on the left, we actually end up with the series negative 1. No, we don't. I need to undo that. We end up with the series of just 1 over n minus 1 from 2 to infinity. This one will turn into the series of just of negative 1 to the n over n minus 1. And so now we only need to determine the convergence or divergence of these two. 1 over n minus 1, that is less than the series 1 over n. It's a larger denominator. And because it is less than 1 over n is a p-series which diverges. By the direct comparison test, we now know that this series diverges by comparison to the harmonic series. This series over here is an alternating series. Stupid phone. I didn't call you. This series is an alternating series. And so the alternating series test is to ignore the alternating series aspect. And first you want to show that the limit of the terms does approach 0, which is true. And then you also want to show that this series would decrease, ignoring the alternating part. So does the series 1 over n minus 1 decrease? Well, if you plug in n plus 1, you have just 1 over n. If you have just the nth term, The n plus first term is less than the nth term, therefore it does decrease. So this one converges by the alternating series test. And therefore I know that we will diverge at -1/2, converge at +1/2. So my overall interval of convergence is -1/2 to 1/2. And there is your answer for the 2012 problem, 10 problem. Which brings us to the 2012 problem. And I may skip a few steps here for the sake of time because it's taking longer than I thought it would. So we have this function, G. We have a Maclaurin series for this. They tell you to use the ratio test. They shouldn't have to, because if you see interval of convergence, you should know that that means ratio test. But we will set up the ratio test here, which again, I've already done. Whoa, how did that happen? You move back. So let's get rid of that. And there is our setup. And now we will reduce and cancel this. So let me do that really quick. So there's our reduced version of this limit, x squared. There were 2 more x's on top than there were on bottom. And x squared can never be negative. 2n plus 3, 2n plus 5. The negative one to the ends will absolute value away. So the absolute values are not needed anymore. And I again have the same degree on top and bottom. It's n to the first. I have 2x squared on top. I have a 2 on bottom. That answer to that limit will just be x squared. And like the last problem, interval of convergence shows that a series will converge whenever the answer to the limit is less than 1, and x squared is less than 1 between values of -1 and 1. Oh, geez, what are you doing? There we go. Now we only have to test those endpoints. So let me set up the series to test the endpoints. And here's the first one. When x is equal to -1, I plug that in. We have -1 to the n times -1 to the 2n plus 1. You can add those exponents. You have 3n plus 1. And 3n plus 1, we're trying to determine, will that alternate still, or will that be always even or always odd? And so let's see. If you think about your multiples of 3, if I plug in numbers for 3, multiples of 3 are 3, 6, 9, 12. Okay, those do change from even to odd. So if I add 1 to that, that will still change from even to odd. So therefore, this series does alternate. And so to apply the alternating series test, we will have to determine if these terms do approach 0, does 1 over 2n plus 3 approach 0, and does it decrease? So let's show that really quick. All right, so it does approach 0. That's a pretty easy one. And then to show that it decreases, I kind of did this one really quick last time, but to show something decreases, the easiest way is typically to show that the n plus first term is indeed less than the nth term. If that is difficult to prove, you could find the derivative of the function that is similar to the series and show that that derivative is always negative, or eventually negative would be sufficient. So this one, my n plus first term would be 1 over 2 n plus 1 plus 3. And that would indeed be less than 1 over 2n plus 3. So the series does decrease. That means we will converge for the left endpoint of -1. We still need to test x equals +1. So let's set that up. All right, so here I'm testing x equals 1. I plugged in 1. 1 to the 2n plus 1 would just be 1. And so we end up with -1 to the n over 2n plus 3. And we're really lucky here because this one ends up also being the alternating series. That -1 on top is really bad. This ends up being the alternating series that we just showed converges. So we don't have to go through the full test again. So this one converges by alternating series test. And so my interval of convergence, we will include both endpoints, -1 to 1.